Okay, I've spent a bit of time talking about convex functions. I'm now going to talk about convex regions. Convex functions being this. Convex region, what's that? Well, I'm going to give an example of a non-convex region first. It looks like this. This is non-convex. I'm talking about the region bound by this line here. And it's non-convex because I can find a point here, x1, let's say, and a point there, x2, join them with a straight line, and the straight line moves outside, it crosses the boundary, and it's got points on it which are outside the region. It's a non-convex region. Convex region looks like this. Doesn't matter which 2 points I choose because the straight line joining them has always got is always entirely within the set. I'm now going to talk about a convex hull. This is quite an interesting idea, and I'm going to link it to the notion of a convex function later. If I've just got some points in the plane here, I'm just going to draw some points here. Then the convex hull, I'll draw it in a different colour. I'll draw it in red. There you go. The convex hull is this, which is there. The convex hull is the smallest convex set containing all my points. And you can see that this point here and this point here and this point here, and I could draw other ones, they're kind of redundant, or they're non-limiting. It doesn't matter where they are. I can move these little points around by a little bit and it won't change the convex hull. It's a matter of some astonishment to me that you can define a convex hull dead easily. Let me say that I've got points x1, x2 up to xn. Then the convex hull is a set of points lambda 1 x1 plus lambda 2 x2. These are to be understood as vectors, I guess, because they're points on the plane, plus all the way through to lambda n xn. These set of points, provided that sigma lambda I equals 1 and all the lambdas are non-negative. So this set here gives you all the points in your convex hull. So now we're in a position to link this definition of convex hull, which is incredibly useful. It's a very nice way of thinking about mathematics, to convex functions. You'll remember Jensen's theorem. Is it Jensen or Jensen? I think it's Jensen. Jensen's theorem, which said that if f was convex, then f of sigma I lambda I xi is, which way around, less than or equal to sigma lambda I f of xi. So what we're saying here is we've got a nice little statement that the function anywhere in the convex hull of a bunch of points is less than or equal to the weighted average of the function evaluated at those points, which is quite nice. I'm just going to give you a couple of examples of this way of thinking being used. I guess really I should be underscoring that because the x's could be vectors if we're thinking in terms of a two-dimensional space here. But I'm going to consider a function f. Oops, I don't know why that happens. I'm going to consider a function f which maps square matrices of a particular size, n by n, I guess, to the reals. I'm going to define f of x, where x is a matrix, a square matrix, equals minus log of the determinant, write that out again, det of x. And this is a convex function. And it's a thing called Cover's theorem, which is very deep and very useful in statistics. But what does it mean? I'm not going to prove it because the proof is quite technical and it goes on and on and on and boring. So f of x equals minus log det x. See, I'm writing determinant in these two arrows. So what does the fact that it's, how do I express the fact that it's convex? Well, I'll just write it out. Oops, what happened there? Oh, here we go. F of, well, let me write out the two case. Lambda x plus 1 minus lambda times, well, call it x1, x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. Okay, so where x1 and x2 are square matrices, and lambda's real between 0 and 1. So that tells me that minus log of the determinant of lambda x1 plus 1 minus lambda x2, the determinant of that, is less than or equal to lambda times log, oh, it's minus log det x1 minus 1 minus lambda log det x2. Okay, so of course, because it's negative, I can turn the inequality around, and I can say that the log of det lambda x1 plus 1 minus lambda x2 is greater than or equal to lambda log det x1 plus 1 minus lambda log det x2. And of course I can play with that if I want to. But the general case is that the log of the det of sigma over I lambda I xi is greater than or equal to sigma over I lambda I log det xi, should be an x, where sigma lambda I equals 1 and lambda I greater than or equal to 0. So you can't draw this because we're in this peculiar space of matrices, but it's quite clear what's going on. Sigma I lambda I xi for some choice of lambda is, or that set at least, is the convex hull of x1, x2 up to xn, where the xi's are square matrices. Okay, and we're just expressing, we're sort of combining, or we're using Cover's inequality about the log of the determinant of x together with the statement, the general statement of Jensen's inequality. That's great, and I'm going to stop there. Really, what I'm doing here is considering sigma lambda I xi, where xi is some object in some, you call it a vector space. Some object in some vector space from which we can form nice linear, form nice, we'll put that in quotes, linear combinations. Okay, the technical word for it is a vector space, but it works for matrices and it works for a whole bunch of other things as well. So what I'm doing is trying to show you that Jensen's inequality and convexity have got nice, not analogues exactly, but they've got nice applications and nice uses elsewhere in mathematics. And I'm going to stop there.